So yeah, welcome everyone to the Computational Mechanics Hackathon presentations. The first thing I want to say is congratulations to everyone on their work. It's super exciting. I think we're all very impressed with the work that was done in such a short amount of time, and it's super fun to see all the enthusiasm around this work, and we're excited to see the presentations. So just a few organizational notes. We're going to be kind of strict about the time limits because of the amount of presentations. At 7 minutes, we're going to say that's 7 minutes. We'll let you finish your sentence, obviously. And then there'll be just a few minutes for questions, not very long. So we ask that everyone reserve questions for the question period, kind of with the understanding that you're totally free at whatever point you want to put questions in the chat, but with the understanding that the chat room questions will kind of be addressed, not during the presentations. They shouldn't even be looked at during the presentations, but kind of in between presentations when people are setting up. And then the other thing is that we'll make decisions about winners in about a week, and then we will email about the top 3 winners. And yeah, so if you haven't received emails about the hackathon, you should definitely let me know, because that means that we don't have your email address. So with that being said, we'll invite people on and they'll show their screens and present. So the first presentation is, let's see, I have the list here. The first presentation is exploring hierarchical structure representation in transformer models through computational mechanics. So if that team could share their slides, that'd be great.
Yeah, should I share my screen?
Yeah, that'd be great.
Yeah. Okay, can you see the slides?
Yes, yep. Perfect.
Great, I'll start. So yeah, I'm Olli Järviniemi with Aus, Rianto, and Konsta and my team. We explored hierarchical structure representation in transformer models through computational mechanics. So the motivation was that in prior work it has been seen that transformers model hidden aspects of the data generating process. In particular, if the data has been generated by a hidden Markov model, then it turns out that the transformers model the hidden states of the hidden Markov model. And the motivating question was whether transformer models can model deep or nested or meta latents. So deliberately leaving this question in a vague form. And to give you some picture of like what we aimed for, the most basic form of thing a transformer could model is learning, for example, a bias. So if the data has been sampled from drawing a biased die, then the model has to learn the probabilities of different outcomes. And then going one level deeper, if the data is sampled from a hidden Markov model, the transformer has to model the hidden states of the Markov model. And then one may ask whether there are still deeper levels of hidden information that we could test whether models can learn and how these deeper latents are represented in these models. So the particular data generating process we looked at was a hidden Markov model whose transition probabilities change over time. And more specifically, we linearly increased some of the transition probabilities over time and decreased the other half of them. So here is an illustration of the data generating process. We have 2 hidden states A and B and different transition probabilities. The first of these numbers corresponds to the probability of outputting 0 and having the given transition, and the second one is for the output 1. And for each input sequence, we randomize which half of these probabilities are increased and which half of them is decreased. And yeah, we basically increase one of the probabilities by some of the probabilities by 1% per input symbol or input length, and decrease the others by 1%. And as a result, the transformer has to model not only the hidden states, so whether we're currently in hidden state A or hidden state B, but also whether the probability, which probabilities are increasing and which probabilities are decreasing. So the value of sign, whether it's -1 or 1 here. And we think that whether the probabilities are increasing or decreasing is, in a sense, a deeper latent than merely the hidden state of the Markov model. And for evaluation, we train the transformer and calculate the validation loss on held out data. And we compare this validation loss to two benchmarks. So one point of comparison is the loss achieved by an ideal Bayesian updater with correct priors for the hidden states and for the value of sign. And another point of comparison is the trivial predictor, which simply assumes that the transition probabilities do not actually change during time. So assumes that diff is 0 in all of these formulas. And for the results, so we trained the model on around 70,000 sequences for 300 epochs. The transformer had 4 layers, residual dimension 16, and we definitely got better than trivial loss. So something like 90% of the trivial loss. And we got essentially perfect loss. So yeah, basically the same loss as the ideal Bayesian updater. In fact, kind of worryingly, we got slightly better than perfect loss, but this is presumably just random noise and maybe some off by 1 errors in loss calculations. And we conclude that the transformer definitely models the deeper latent of which probabilities are increasing and which are decreasing. We also try to find geometric representations for these probabilities of different hypotheses via linear projections, but we were unsuccessful, so we couldn't find projections that actually resemble the true beliefs by an ideal predictor. But we didn't have much time to do this, so this is far from conclusive evidence that this does not happen in the models. And it would be nice to have a more systematic study of this type of thing with these deeper latents. And yeah, that was it. So now would be time for questions. Yeah, thanks for listening.
Great, thank you. I had a question.
Go ahead.
I was wondering, did you try looking at all for the belief structure for the base model where you set the dynamic, kind of the latent to 0?
Yeah, we tried to do something in that direction, but we, unfortunately ran into time constraints and implementation errors. So yeah, we were unsuccessful here.
Great. If anyone has any other questions, feel free to ask them.
Yeah, I also have a question, but also people should feel free to put their hands up, maybe so we can organize questions. But yeah, Ollie, thanks for the nice work and presentation. So I guess when I see the kind of the data, the stochastic process that you've been training on, to me, I'm wanting to characterize that as a non-ergodic process because the sequences are kind of characterized differently. So it's both non-ergodic and non-stationary. So it's nice to confirm that transformers are indeed tracking this. But one of the things I wonder is in terms of how you go about identifying the ground truth geometry, because I guess it shouldn't just be the things over A and B, I would think, because I would think you'd have all these different states from all these different non-ergodic components. So I'm wondering which way you went about that.
Yeah, I'd characterize the kind of hidden information, in this case, to be 2 bits. So a total of 4 options. One is which of the current hidden states is the one we are in, and another one is the value of sign, which we sample randomly from -1 and 1. So you can completely characterize. Yeah, you can basically all of the information you need to track is the current hidden state and the value of sign. And you can assign probabilities for each of the 4 resulting hypotheses and do Bayesian updates on those. And that should give you a 3-dimensional simplex, which you can then visualize.
Gotcha. Yeah, cool. Thanks for clarifying.
Thanks.
It looks like we have questions in the chat too, right? From Jay, why 300 epochs and not more?
Yeah, we focused on having lots of different sequences, and the number of sequences times epochs is the relevant variable here. And we didn't do more because we basically got like as good performance as you get out of the model with already like 100 epochs or so. Or let's say, yeah, some millions of sequences, or sequences time epochs. Even so, that's what I don't think it basically matters for the results if you had more.
Cool. Yeah, thank you very much.
Thank you.
Very interesting. We'll move on to the next presentation, and the next group is handcrafting a network to predict next token probabilities for the random-random-XOR process.
Great, let me share my screen. Give me 1 second. Okay, can you all see my slides?
Yes, perfect.
Awesome. Well, let me start my timer, then I'll get started. Okay, so hey everyone, I'm Rick. Today I'm going to present my work, handcrafting a network to predict next token probabilities for the random-random-XOR process. I want to start by just going over what is the random-random-XOR process, and I'll explain why I did what I did and what exactly I did. So this is a hidden Markov model. We have 5 different states. The fact that it's a hidden Markov model means we don't know, we can't directly observe the current state at any given time, which also means we don't know the start location of our process. This is a random-random-XOR process, which means from the center state, and again, we might not know if we're at the center state or not, but if we're at the center state, we'll generate 1 random bit followed by another random bit, and the third bit we generate will be the XOR of the previous 2 bits. So say we start at state S, state S in the center. I don't know if you guys can see my mouse, but if say we generate a 1 randomly, then we generate another 1 randomly, then we know the next bit generated, if we had started at the center state, will be a 0, because that's the XOR of 1 and 1. Regardless of what bits we generate, if we're at the center state, it will always take 3 moves to get back to the center state, which means this process has period 3, and we'll be using that property in a few slides, as you'll see. And then I just want to note that Simplex, the organizer of this hackathon, they trained at least 1 network on the outputs of this process, and they found that the 36 possible belief states or different probabilities spread across the 5 different states. And I'll just come back to that in a few slides as well. So what did I do? So I wanted to handcraft, that means manually set the different network weights for a 2.5-layer transformer to calculate the next token probabilities for this hidden Markov model. I want to do this for a few reasons. One is, I think it would be awesome to interpret the network that Simplex has trained on this hidden Markov model. But I thought it would be a little bit too much to do it in just 2 days for the hackathon. So I wanted to think about what are some possible features that might be worth looking for come the future. And then secondly, from an AI safety overall perspective, we don't understand how these models work. My dream is that maybe at some point we'll be able to replace components that we don't understand with components that we built by hand that we do fully understand, to slightly reduce the potential of risk and make our models slightly more interpretable and maybe make it easier to interpret the parts that we don't know. So yes, let me explain what I mean, what I did by handcrafting the network. I don't have time to get into the full algorithm, what each layer, what each block is doing. I want to touch on one important component in my crafting, which is this notion of an XOR violation. So think back to this network. As I said earlier, it has period 3. That means that the XOR will occur every third point. We don't know if that will be at points 3, 6, 9, which is what I'm going to denote as the green right here, or at points 4, 7, 10, which is what I'm going to note as the blue right here, or at points 5, 8, 11, which I'm going to note as the red points right here. And my network's going to try to figure out, is the XOR occurring at green, or is it occurring at blue, or is it occurring at the red points? And maybe the network will know for certain that it's occurring at green, or maybe it will know that it could be occurring at green or red, but not blue. And that's essentially what my network that I'm handcrafting is trying to calculate. Let me show you an example. So let's say the ground truth, which we don't know, is that the XOR is at the green point, so the third point and the 6th point and the 9th point will be green. When the hidden Markov model is generating its tokens, it generates 2 tokens to start with. Don't worry about those. The third token is at the green square, and it's 0, which is in fact the XOR of the previous 2 tokens. So that means green is still a possibility of the XOR location. Then let's take a look at the next location it generates, which is blue, and so 1. 1 is not the XOR of the previous 2 tokens, which were 0 and 0. So now we know that the location of the XOR is not blue. Maybe it's green, maybe it's red, and we can use Bayesian statistics to figure out what's the relative likelihood that's green versus red, given what we've observed so far. But the main takeaway that I want you to leave from the slide is we know that the XOR location is not the blue location. So when I'm handcrafting the network and I have the full architecture on the left, like I said, I don't have time to go through all the steps today on the left, but I want to just highlight a few steps from the right side. So we take the rollout of, or the bits that we've realized from our hidden Markov model. The very first attention layer is going to attend to the previous 2 tokens. And then the MLP layer after that will calculate these XOR violations based on its current token as well as the previous 2. It will find that some locations are violated while others are not. Then in attention layer 1, these XOR violations will be shared with future potential states, future potential positions. And then the next 2 MLP layers will use this information and these Bayesian statistics to figure out what's the probability that we're at the XOR location. Maybe it's 100%, maybe it's 0%, maybe it's 66%. There are a few other possibilities as well. And then given those probabilities, it will then figure out what's the probability that the prediction is 0, what's the probability that the prediction is 1. And again, I have more details in my write-up and actually go through how the residual stream changes with each of these blocks. But like I said, I don't have time to get into that today. I did a few other pieces of work. So I wanted to check that if I did it actually works. So I built a ground truth simulator and confirmed that the calculations from my simulator of this hidden Markov model match the outputs of my network. And then secondly, I took the starter code from Simplex and I tried running the linear regression and then plotting the PCA of the 3 most important dimensions. I didn't find the triangular simplex-like structure as clearly, or I'd say I didn't find the simplex structure that they found when they ran this on their model trained on the same Markov model. But I did find kind of a triangular-like structure in the third plot here. I'm not sure if this is similar to what they found or different, or just noise or something else. That's something I want to dig into if I had with more time. I realize I'm running low on time. I think the main takeaway I want you to leave this presentation with is I successfully handcrafted this network, and I didn't need to come up with the full belief state that Simplex did when they were analyzing their network. I only need to figure out what's the probability that we're at an XOR location and what should the next token be if we are conditional on being at the XOR location. So maybe we need the full belief state, or maybe we just need to know a few important features when we're analyzing models that are trained on hidden Markov models. And yeah, out of time, but in the future, I'd love to actually try to interpret the model that Simplex has trained and see if I can find any of my features or if I can find the full belief state and see if how those causally affect downstream output. Yeah, thank you very much. I'm happy to take questions.
Great.
Thanks so much, Rick.
That.
Yeah, it was really nice. I feel like that's an important direction for us to go. I mean, we found the as you mentioned, we found these belief states, but there's been this open hypothesis whether transformers actually have something like a Bayesian updating circuit or not. And I feel like there's an important step in the right direction.
Thank you.
Maybe a quick question while others are thinking of theirs. You say something about in an MLP layer, it just MLP does Bayesian updating. It feels like there's a lot packed into that statement. So I was hoping you could help me understand it.
Let me share my actually, let me share my code. It's probably a little too much. But I guess like the short takeaway is there are, I think, 13 possibilities to think about. And I just hard code in each of those 13 possibilities. Let me see if I can easily pull up my code. I'm not sure I'll be able to find it. Let me see. Can you see my code?
Yes.
Okay. So yeah, so essentially I like do the Bayesian updating math by hand and figure out if, and like my labels are different than what I had in the presentation, but essentially this says if green, red, and blue are all still possible and we're at the green state, then it's 1/3 probability. If only green and red are possible, then it's 1/2. If only green and blue are possible, then it's also 1/2. If green is impossible, then it's going to be 0, which is coming from here. If green is possible, but red and blue are impossible, then it's going to be 1. So those are like, that's for green, and I have similar constraints that are a little bit more complicated for blue and for red. So I'd say like the Bayesian updating is hard coded.
Dig into this a bit more.
What do you say?
But yeah, you're hard coding finding the weights in the MLP that'll do it.
Correct. Yes.
Gotcha. Great. Thank you.
Yeah.
Okay, great.
Awesome. Thank you all.
Yeah, thank you. So the next presentation is, oh boy, steering models belief states. So if that group could share their screen.
Is it working?
Yep, thanks.
All right, everyone can hear me? Everything's fine. All right.
Yep.
So I'm Sinan. Thank you all for taking the time to be here today. I'm going to share with you some work I did together with my teammates Gonzalo and Talasso on how we can steer a model's belief states. So alignment is a major AI safety issue, and pop culture is just filled with myriad nightmare scenarios of how much can go wrong. For example, in the iconic scene of 2001 Space Odyssey, our human protagonist Dave is asking Hal, the AI, for re-entry onto the spaceship. And he says, "Open the pod bay doors, Hal." And Hal chillingly responds, "I'm sorry, Dave. I'm afraid I can't do that." And so why? Well, it's a bit awkward, but suffice it to say that Hal's got some problematic beliefs, and wouldn't it be nice if he didn't? And is there some way that we can change Hal's beliefs about the world? And so our goal was to steer our transformer behavior by steering its belief states directly. And so we've learned, we heard from the keynote lectures, right? Computational mechanics tells us that there's a huge difference between a generative and a predictive process, mainly that if you have some generative HMM, it's not enough to know the generative structure for prediction, and that the prediction process is actually another HMM that has not only the generative structure, but also has these transient states. And these transient states are supposedly very important because these are going to be because with like increasing observations, the model is going to need to update its beliefs until it's fully synchronized with the world state or the generative process, right? Synchronized meaning that the model knows 100% that the state the generation is in. So now the MSP, right, also has this beautiful geometric property that the states can all live on a simplex. And what Adam and Paul showed us is that this belief geometry, at least for some of these toy models, right, are already, we can start seeing them in the residual stream. So what we want to do is to see if we can causally intervene and steer these toy transformer from one belief state to another, and if this is sufficient to control the model's behavior. Okay. Just because I didn't time properly, can you tell me how much time I have left or how much that was?
You're at 2:30.
Okay. Okay. So how are we going to steer? Very quickly, we can steer via the mean activations, and this is just by, projecting these vectors and getting their difference, or we can steer directly using the internal geometry and calculate the direction in this inferred simplex, and then we can project back into the residual stream. So let's see what we found, right? So here we're looking at how well our intervention worked for moving between T and F states. So quick note about the plots. The green bars are the probability of outputting 1, red the probability of outputting 0. Each bar graph has the same 4 elements on the x-axis, so the original 2 states and what they should output, and then what we got when we tried to steer them, and each of the columns when we tried to steer by layer, and then when we tried to steer using the activations across all the layers. And so the main finding is, right, so if we're like this blue box, right, if we want to go from S to F, those are going to be these blue arrows. And our main finding here is that, we can steer the model by using the belief states, and but it seems to be more successful in the later layers, and averaging across all layers tends to reproduce the results of working on the later layers. And so then our next thing was, okay, well, we have these activations along the in the activation space. What do these steering vectors look like if we project them back into the simplex? And so you have like 3 different scenarios here, right? When we're going from 0 to 1, and from true to false, and from true to 0. And we can see that basically the direction and the magnitude of the vectors don't really align with what we might expect. There's an overshoot or an undershoot in the magnitude, and there's an overshoot in the magnitude, and the directions aren't necessarily what we would expect. And also, when this direction is completely aligned, we don't necessarily get a 50-50 output, which we would expect. And our true false or TF states, that we have, the direction and the magnitude don't fully align. So we're wondering, okay, well, what if we did align them now and we got these aligned states? What could we improve, and what would the results be? And basically, it turns out that when we use when we use the simplex and then project back into the residual stream, it sometimes works and it sometimes doesn't. So this is a true to false thing, true to false steering that we're trying. If we use layer 0, 1, 2, 3, we see that we get no steering. But if we, but if we just use the last 2 layers, then we start to see this output probability distribution that's a little bit more aligned. So just a very quick reminder that this is the opposite of what we see when we do with the activations, where averaging across all layers actually gives us a good output. Here, using more layers, using the earlier layers seems to kind of make the behavior worse. So the next steps would be to investigate the steering vectors, especially in this belief geometry space. Is there a better way to steer using the belief geometry? Can we predict when a steering vector will be successful? And also, can we track the updates between the belief states of the model and use them to find better steering vectors? And lastly, another question we could ask is, how are the parts of the belief state distributed over the layers, and is there redundant information? Okay, so our key takeaways are that we could successfully steer the transformer from one belief to another, that these activation-based steering vectors did not seem to perfectly match up with what we might expect in terms of the direction and the magnitude in the inferred geometry space. It was more difficult to steer the transformer using the belief geometry space rather than the activations directly. And so we think that, okay, like there's definitely like evidence that the belief geometry is existing in the residual layer and that it can be used for intervention and control, but it doesn't seem to be a complete description of what's going on. Either we're not taking full advantage of the geometry, or the transformer is doing something more that is not explained by the geometry alone. And so thank you everyone for listening, and for the organizers for organizing the hackathon.
Thank you so much. Yeah, I think this is yeah, causally testing the geometry seems super important. I was wondering, could you just say quickly how you computed the steering vectors?
Yeah, so for the activation, we have a hold on here. Okay. So we know that, like, we know for each belief state what the average activation is. And so for each belief state, we have an associated activation vector, or an average one. And then as we try to steer from one to the other, we're basically subtracting the two means of the activation vectors, and then that gives us the steering vector, which we then go and we add back to, you know, from wherever state we start. And then for the other one, we basically, like, in the simplex space, we just calculate the 4-dimensional difference of, or 5-dimensional difference between the, like the two 5-dimensional vectors, and then we try to project that back into the residual stream using the pseudo inverse of the transformation matrix that got us the that the linear
Great.
regression gave us.
Yeah, thank you. That makes sense. I think Keenan had a question.
Yeah, so if I understood you correctly, you were just observing, like, you do your steering vector, and then you look at the effect of the prediction on, like, that same time step, right? The immediate prediction.
Yeah, so it's always on the last token that we're
The last
predicting.
token, yeah. So
Yeah.
it seems like it would be cool instead to, like, you know, you do something at one time step, like try to make it believe that it's at the beginning of the RNNs process and has received a 0, and then see what effect that would have at later time steps that are not the very next prediction, right?
Yeah, I think that would be, like, something cool that we could try it.
Yeah.
I think, is Gonzalo gonna add something?
Yeah, so if I can,
Yeah, of course.
I did try to do exactly what you're saying. The problem is that then you don't know what is the ground truth. Like, after you do the steering, you lose what should be the ground truth of what's happening, because when you do steering, the model will output a token. And if it is not a token that is valid for the XXXOR process, then you stop being able to track where it is. And so you kind of lose everything. I started doing something like that, and then I just couldn't figure out how to make sense of what we were doing. So we focused on only doing it at the last token position, because we knew that whatever output we were doing, it was going to be a valid output.
Okay, I think that's time for this presentation. Thanks again. Our next presentation. Oh, sorry. Yeah.
I'm sorry. I'm just trying to stop sharing. Okay, perfect.
The next presentation is RNNs represent belief state geometry in hidden state.
Where's that share button? Here it is. Okay, can you see my slideshow?
Yes.
Okay, so I made my slides really short because I like slides that basically just show, like, the result, the picture. So I basically, like, reproduce the main results of this thing on transformers, but instead of using transformer architecture, use, like, vanilla RNN architecture, which is, like, an older thing. a lot of people already know this, but like the difference between RNN and the transformer is transformers have these special attention layers so that it can pay attention to like a specific token that's like 100 tokens back in the stream or something. So that makes it, you know, very scalable and efficient. Whereas RNNs, they have this kind of architecture. I'm using a multi-layer RNN. So you have the same kind of process at each step. There's these different, you know, MLP layers, but there's no attention layers. And so if something wants to propagate from the past to the future, it has to do it one step at a time. And the things that each layer outputs that go to the next layer are called the hidden state. And so my overall architecture was you have the multi-layer RNN, and then to get the token prediction, there's just like a fully connected linear layer that takes the hidden state produced by the last layer of the RNN, and just it goes to the number of tokens that there are, and then there's the softmax, and the softmax gives you the prediction, like the probability of the tokens. And so yeah, I just trained. I used two different Markov models. There's the RR-XOR one, and then there's some version of the MES3 process, which is that symmetrical. There's three different states and three different possible output tokens. Yeah, and so I trained it. It got pretty good loss. And then I did the same kind, the original thing was doing a linear regression, seeing what directions in the transformer residual stream approximate these belief directions the best, and I did what directions in the hidden state do it. And so without further ado, here's the results for the RR-XOR process. So here's what we would expect it to be if it were doing the mixed state thing perfectly. And then here's what you get for each of the three layers. So I ended up selecting the hyperparameter of number of layers to be 3. So there's 3 different hidden states, the output of each layer. So if you do it like with only the first layer, clearly it doesn't match up that well. It looks like, just kind of random. There's maybe some of the extreme ones are in the right directions, but it's just like a blur. There's no geometry you can see. And the same with layer 1 and layer 2. But if you do the linear regression on all the layers of hidden state concatenated, then it looks just like it, right? So clearly it is it's storing the beliefs about the hidden state in a linear way, because we can see it as a result of this linear regression, just like the transformers are doing. It's not some weird, more complicated thing, but we can see it in this linear projection. But it's distributed over the different layers somehow. Yeah, and then here the MES3 one gives this cool fractal. So this is the ground truth, what we expect to see for the particular parameters of this MES3 process. And for this one, I showed how it changes over the training. So at a point pretty early in the training, after only like 1,500 tokens, this is what you get. So you can kind of see the fractal. It's just kind of blurry and wavy, and you can see it a little bit for the hidden state of each of the 3 layers. And you put them together, it's definitely starting to look like the fractal. And then if you go much later in training, it really sharpens up. And so this is like a really nice looking fractal, and you can see there's some pretty faithful representation at each of the layers. So, and to my eye, it kind of looks like the hidden state output by the last layer is kind of more faithful than the first layer, for example. And for this particular process, that kind of makes sense, because in this one, there's no like redundancy. And if you have enough information to give the next token probability, then you also know exactly what the hidden state is. There's no degeneracy. Yeah, so this is important because the computational mechanics stuff in theory should apply to any kind of model you train that's capable at predicting the process evolution. And the belief states are going to be in there. They might be in some weird way, like a nonlinear thing or something that's hard to interpret. But they should be in there. And then this is an example of like some architecture other than transformer where we looked and saw, yep, they're in there linearly. Any questions?
Great, thank you. I was just wondering, were you expecting this to work?
Yeah, I thought it was pretty likely it would work.
Okay, cool.
Yeah, because like what an RNN is doing is actually simpler than what a transformer is doing, right? Because it's not looking back like arbitrary steps in time to what the attention says. It's really just looking at the previous time step. And so, it's kind of more likely that this would do this than a transformer would, in my belief.
Yeah, that makes sense.
Yeah, really nice work, Keenan. Thank you for that. Yeah, I also had the expectation that in recurrent neural nets we would find this, and like it like even more so should be there, but we never actually checked. So it's really good to see this.
Right.
I have a question. If you have any intuition about maybe across different architectures, if you would expect similar representations across layers, because I guess the way that you're finding between the MES3 and Random-Random-XOR, the way that it's spread across the layers, it feels similar to how we were finding it for transformers, but I don't really have a good intuition for it. So curious if you have some perspective on that.
Yeah, I noticed that too, right? Because you had the same kind of thing where in order to get this picture, you had to concatenate the different sort of layers of the transformer together, right? And if you didn't do that, it was more messy. And so, yeah, it kind of, there's a way that makes sense to me, because like if you think of the computation you have to do, like what the minimum like computational graph or whatever is, like there's what state you think it's in, and then for a general process that doesn't directly give you the output probabilities, but you have to do some other kind of steps in there. So yeah, it makes sense that for like a special kind of process like MES3, that it might be in all the layers or the last one, but if you have to do more processing on them, it makes sense that it's not just going to be in. I mean, it might have made sense if it were like only in the first or second layer, but that's not what we saw.
Cool, thank you.
Maybe I'll ask one final question. I was wondering, are there any other architectures you think would be kind of the next obvious best thing to test out?
That's a good question. I mean, there's like I've heard a bunch about Mamba, and I don't really know what to do with that is yet.
Yeah. Cool.
I thought that I might have to go to like a LSTM or something to get good performance, but I didn't have to.
Great.
Okay.
All right, thanks again. The next presentation is belief state representations and transformer models on non-ergodic data.
Hi.
Hello.
So let's see. Doruk, do you have the presentation ready? Should I do it?
Sorry,
No problem. So our project was mainly about doubting Adam and Paul. So you two are nice guys, but we thought this can't be happening in like large transformers. So clearly, right, the real world is totally different from what we see in these toy models. And one important way, I hope we get the screen working. I can't see it yet. Right. One important way the real world is different from our toy models here is that they're non-ergodic. So that means, for example, if we have a token in English, that's not going to be reached from a token in Korean, for example. So we want to construct processes which have this property. So we want to disconnect the hidden states and then see what happens. So essentially you want to falsify it, and we expect it not to get anything much working or to get them a bit more disconnected, but let's see what actually happens. I think the screen takes a while, so I'll just do that. Oh, there we go. Wonderful. There we go. Very nice. So our main questions was like, where can these belief states show up for non-Nonergodic data? And if they do, how will they look like? And we constructed 3 processes, which are very easy toys for this. So next slide, please. And one of them is just meth3. So maybe you can do full screen too. With meth3, you have the nice simplex, right? And we just disconnected the hidden states so that we can transition from one to the other. Meaning we should actually not get any benefit from inferring a belief state much, right? I mean, if you, for example, see a lot of token A, you just have to predict token A and then you're done. If you're the transformer, your job's very easy. You don't need to do Bayes' rule. And then we did the same thing, but with 2 outcomes, so weighted coins. So 2 instead of 3, and 1 coin is fair. So one is literally just coins. The transformer has to guess which coin it's looking at, and then predicting what it thinks is most likely to happen, which is a human way to frame it, of course. Linear algebra might do it differently with the stochastic gradient descent. That's our job to find out. And then in the middle example, we also marked one side of the coin with tape, let's say, so that you can discern, okay, this one is marked, so it's the one biased coin, whereas the fair and the other things indistinguishable. So please have a guess. What do you think might happen here? Maybe, I mean, you've thought about this stuff, so I wonder what you think about this. And one doesn't work at all. It will be interesting to see. So next slide. We trained transformers and we were compute constrained. So we trained tiny Q transformers with 1 layer, very small attention heads. It's crazy that this stuff still works. This contradicts sort of my understanding of transformers, and the context length also very short. Next slide. Yeah, so we just basically repeated the less wrong setup, right? To produce the like a regression of belief states. Everyone here probably has done something similar, so no need to dwell on that for too much. So let's see. This result is very surprising, I think. So we think this means, yes, it actually found a belief space geometry, like it's linearly in there. And that's so weird. Like, I don't understand. Like, you just have to count and then you're done. But apparently here, even when there's a simple algorithm, just selecting the most common token, there's no dynamics, no if this then that. It still, I think, wants somehow to do it with Bayes' rule. Is that what's happening here? Please tell us about this. Like, this is crazy. So here we're returning to sanity a bit more. We predicted this one. So with a fair coin, right? There's really no reason to learn a fair coin in any way. Because let's say you're the transformer and I tell you, okay, you're looking at a fair coin, what are you going to do? Like heads, tails, it doesn't matter. There's no way to have any policy. And then with the one marked side, then we get to linear subspace, which is also interesting, like decompose this more sparse belief space into 2, which we think is what's going on here. Like, it's very easy to overinterpret these sorts of results, especially us, but yeah, anyway, so that's, yeah, we learned a lot. We didn't know anything about transformers, and now we're smart, and we know about CompMech. That's what this slide is about. Thank you for the opportunity. Next slide. So, okay, let's see. What can we do here? We would like to do some math. We didn't do any math. Like, for example, the decomposing the sparse structure into 2 linear subspaces. How does that happen? Why does it happen? Can we like get someone who knows more CompMech than us to understand that? Is that expected? So we were able to predict some stuff, which is nice, but that one is not cleared up. Also, we didn't try transient states, which is an obvious like thing which happens. For example, in GPT, you have always the like start of conversation token, end of conversation token, these like that only happen once and so on. And so next slide, please. So tentatively, we said, okay, Adam and Paul, you might actually be right on this specific issue, and there is apparently, even if you have a non-ergodic process, it still finds something in there for very, very small transformers too. So very like tight conditions we're operating under. But yeah, crazy stuff. Thank you.
Great, thanks a lot. If anyone has a question, please jump in.
I think we're sort of the ones with the questions.
I'll ask one. I'm wondering, do you think that things can change with like more layers? Like maybe maybe one needs a certain amount of layers or something
For what to happen?
in order to perform a task well and to represent the full simplex structure?
For the third one, yeah, I think that could happen. That could be what's happening here. For the first two, well, it already did sort of what we expected, and there's no potential beyond that. Yeah, that could happen. And like one corner looked a bit nonlinear, I guess. It would make sense from what my understanding of CompMech says here, that it actually does learn that, for example, there's not much to guess in that top left corner. I don't know. Yeah. But probably yes.
Cool.
Yeah, thank you for the nice work. I feel like moving in the direction of non-ergodic processes is indeed important, and so it's nice to have some work in that direction.
And some stuff breaks. We were also demonstrating that, right? Something.
Yeah, exactly. So it's good to know where it breaks. Yeah, I guess one comment you made that I'm curious about is you're saying there's nothing to learn with like a fair coin.
Yes.
I guess I don't share that perspective, so I'm a little curious about it. Maybe it's that like even when you initiate a model, everything's like as fully random as possible. Usually, maybe that's the intuition. But I don't know. I mean, I guess you still need to nail that probability distribution somehow.
Yeah, so I'm embarrassed to say that I spent at least an hour thinking about predicting a fair coin. And this was my conclusion because, I mean, you have to, like, stochastic gradient descent has to work with something here. Like, there has to be some information. And I like it. You can bake something into the training process, of course, that will chisel like a structure out of nothing. But like just from information theory, right? What are you going to learn here?
Yeah. I mean, I guess I would say like you randomly initialize the weights of your model and it's going to make some prediction. And maybe it was like 46-54 bias. And then it's like, oh, it has to correct for that. So I guess it's learning, but it's not as exciting.
Why? No, like, okay, we have to talk about this some other time, maybe, but I like.
Yeah, we can talk about it offline.
Any policy in terms of any. Okay, yeah.
Yeah. Thanks a lot for the presentation.
And thank you for the opportunity.
Yeah, cheers.
Great. Thanks again. The next presentation is investigating the effect of model capacity constraints on belief state representations.
Yes, let me just share my screen real quick. Okay, can everyone see this?
Yes.
Okay. Oh, shoot. Okay, so my name is Chu Chen, and today my teammate Ari Brill and I are going to talk about investigating the effect of model capacity constraints on belief state representations. So what is the motivation for this project? Basically, so far, computational mechanics has looked at predicting the internal structures of models that optimally predict data sequences, basically. But so far, it's been looking at memorizing networks, and it's sort of assumed that that all aspects of the data are worth modeling. But in reality, when we're looking at realistic networks and the ones that we would really be interested in studying, we oftentimes these networks are not pure memorizers. They generalize, and they learn a model that's simpler than the data in order to facilitate that generalization. So I sort of have some definitions of abstraction, generalization, and approximation up on the slide. And I think these are all components that we see in language models today. I also have this picture. Basically, sometimes you don't want to be on the right side, like learning every feature of the data, but you instead want something sort of simpler and smoother that will generalize better. So in order to try to extend computational mechanics in this direction to be able to model generalizing networks, the idea is maybe we can just look at the residual stream simplex in a generalizing network and compare it to the predictions that computational mechanics makes for an optimal predicting or memorizing network. And we can basically see, okay, so how does this residual stream simplex differ? Do we notice any patterns here? One prediction would be that the generalizing network has a sort of coarse-grained version of the theoretical prediction. We're not really sure. This is something that we were interested in looking into. And in theory, it would probably be best to measure the generalization using a training and test set. But given the limited time of this hackathon, we wanted something that would get going more quickly. So instead, we just tried varying the weight decay, which is basically this regularization term that is pretty similar to L2 regularization. And it basically incentivizes the network to be simpler, and it tends to improve generalization. So basically, we change up the weight decay, and we look at the residual stream simplexes for different weight decay values on the presumption, sort of, that this is kind of akin to using networks that are progressively more abstract and generalizing.
All right, great.
Yeah, Ari will take it from here.
All right, great. So if you can hear me, I'll talk about the training that we did and the results that we got. So basically, yeah, we trained a series of models with increasing values of weight decay. And to do that, after developing a training pipeline, we first wanted to make our models as small as possible while still getting good performance. And the reason to do that was both so we could train more models faster in the hackathon, and also because you would think that having a smaller model, then it might be easier to constrain the model capacity. And so the main thing that we did is that we used attention-only transformers, so essentially no MLP layers, and for our models that reduced the parameter count by a factor of 3. And then we trained our models on 5 million samples of data from the MES3 process. So this is a process with triangular fractal geometry. And then we extracted simplex representations at multiple checkpoints in training. We trained models for a series of weight decay coefficients with no weight decay, 0.3, 0.5, 0.7, 0.85, and 1. Next slide, please. And so what we found is that increasing the value of weight decay leads to more coarse-grained belief state representations. So here on these plots is after after training is complete, starting with no weight decay in the top left, where you can like resolve by eye. There's like 27 distinct triangles. And then as you increase the weight decay to the bottom right with a weight decay coefficient of 1, that it's much more coarse grained. You can only really see like 3 large triangular structures. Next slide, please. And then we also looked at how the geometry evolved over training, because we wanted to ensure that the models had converged and pick out any interesting phenomena. One thing that we did note is that with weight decay, sometimes we found apparent phase transitions. So you can see this in the second row on the third column, which, by the way, is going epochs left to right, and weight decay increases from top to bottom. So sometimes the geometry would blur before re-equilibrating. And so we aren't really sure why this is. One possibility is that it could be related to a time scale for the exponential decay of weight decay to take effect. Yeah, so these are our results. And so for next steps, we're excited to use these techniques for constraining model capacity to do more detailed studies of generalization and approximation in neural networks, and using the tools of computational mechanics. All right, thank you very much for your attention.
Great, thank you.
Yeah, really nice work. Thank you. Thank you both. I have just like a silly technical question. Chu, you said that weight decay is like L2 regularization. How is it different?
So I
I think I should know
believe.
this.
Oh, so I'm actually not completely sure about the answer to this. It's just sort of a term that I assign a number to when I write my code. But I think the idea is in L2 regularization, I think at every time step you apply a penalty with your update. Or I don't know about time step, but every time you update, in addition to your error term, you also have this L2 normalization term. But I think for weight decay, you sort of like gradually decrease the weights as you go through training.
Can I add to that?
Yeah, sure.
So in L2 regularization, you add a term to the loss. So in that way, you update the gradient because you just add an extra term to the loss. In weight decay, you update the values of the weights directly. So if you have just SGD, those are just 2 ways of saying the same thing. But if you have an adaptive optimizer like Atom, then they interact differently.
Awesome. Yeah, thanks for clarifying that for me. I'm also curious if you would want to say more about the phase transition that you see. You said maybe something about time scales there. What's being traded off here? I guess usually I see like a phase transition as sometimes like a conflict between 2 things.
I think it's a trade-off between accuracy and simplicity, because the weight decay incentivizes simplicity, but you also want to be able to accurately predict the data.
Yeah, makes sense.
I was wondering, do you have any ideas or thoughts? They don't need to be super specific about kind of what would be the next types of experiments or things you would think about to kind of get to these things that have to do with generalization versus memorization and how they relate to simplex structures.
I think it would be interesting to have some noisy data, and you take the HMM that would like perfectly generate the noisy data, and you like extract what the MSP would be for that. And then you also think about what the HMM would be if you remove the noise from the data and get the MSP for that. And then when you train your model, you see how well it generalizes to unseen data with, I guess, like a different, different noise values. And you see where the simplex is in the residual stream compared to the like noisy MSP versus the like smoothed out MSP. And one would assume or like guess that as you generalize better, you get closer to the smoothed out version.
Well, yeah, I like that idea. If there are no more questions, we can thank the speakers one more time and move on to the next presentation.
Thank you.
Thank you. The next presentation is
Hi.
looking forward to posterity. Oh, hello.
Yes. All right. I think can people hear me?
Yes. Great.
All right. My presentation is looking forward to posterity. What past information is transferred to the future? So my motivation for this project is computational mechanics makes predictions about the structure of the computation that's performed by neural networks. So something that I was interested in doing is seeing what information they look at when they make predictions. So how I wanted to do this was I wanted to see what attention heads paid attention to, and then from that we can see like, okay, so then what's their function? How do they like contribute to the prediction? So for this, I think that it's very valuable because if we can find out if we can create like methods by which we can find like say each circuits for the circuits for the attention heads, right? Like if we can find out what each one of them does in terms of prediction, then that really can bridge mechanistic interpretability and computational mechanics together. As in like we would be able to attribute what each node and vertex, what components of the neural network factor into each one. So for what I did, I took the Random-Random-XOR transformer since it already has been trained and it also already has a well-defined structure. So I used transformer lens and circuit viz for it. There's a link to my code there. I think maybe I can just, it's also in my submission. So here, I was able to visualize all of the attention heads. The transformer has 4 layers, each with 4 attention heads. So for this one, you can see, you can mouse over and you can see what each attention head pays attention to when that token is current. And you can actually, this is actually interactive. You can go and look at it. I'm just going to show it for a moment here. Oh goodness, where is it? Okay. Yes, so if you go and look at the notebook, then you can see, you can mouse over and then you can see which tokens they pay attention to, and you can also look at the different heads. So if you're interested in that, then you can go and look at it. The other thing that I wanted to do was, okay, so in terms of the function of the attention heads, there are 2 things that are interesting to me. The first one is I wanted to look at which attention heads pay attention to the previous 2 attention heads, because that's how you compute the XOR, right? It's the XOR of the previous 2 tokens. And I also wanted to see, given that, how do they find out where the loop starts, right? Like what with Keenan's presentation went over, like where the loop starts is an important thing for the model to pay attention to in order to predict the outputs of the HMM. So here, I found that this is actually like a curious result where depending on the input, then it will change which ones are the current and the previous 2 attention heads. For this, I calculated like based on a threshold of attention. And I think this is because of the small context window. I think if the context window was made longer, then it would have more separation between the attention heads. So the interesting thing here is that there are no layer 0 current attention heads. All of the previous 2 tokens attention heads are in layer 0, except for 2.2, which is like so anomalous. I don't know what's up with that. And earlier layers pay more attention to previous tokens than later layers. And I thought that was so interesting because normally the typical finding is that later layers do more complex processing than earlier layers, but that could just be me making a wrong assumption, and it's actually that the earlier layers are actually the ones that are sort of like counting to 3, I suppose, and then like it's the later layers that do the XOR. And for future work, something that would be interesting to build off of this is, well, what we want to do is more concretely assess what each head contributes in processing. And given that, what the behavior of each head changes depending on the inputs, then looking at like more permutations on the inputs would be valuable. I only looked at 3 for this project. And the other one I wanted to see was, is it possible to visualize the effect of each head on the belief states? Like, for example, like the 2.2 or like the 0.1 head, can I ablate it? Can I set all of like the weights of it to 0? And then like, how would that change? Like given that causal intervention, given that intervention, how would that change like the performance? How would that change like the belief states? And like the hope that I have is that like in the future, computational mechanics might function as a higher level form of mechanistic interpretability that's more abstract and more scalable. And because here, right, it's very like, I had to do all of this by hand, but if we could somehow like make some sort of like theory where we could abstract over things like this and like, predict how each neural network would work based on more first principles, then that would be like a very valuable for alignment. Thank you. I'm like, if anyone has any questions, I'm ready to answer them now.
Great, thanks a lot. Yeah, it's fun seeing the attention patterns like that, because as far as I know, no one's looked at them in these types of comp mech tests.
Yeah, I thought that was like an underexplored opportunity. It's definitely popular in mechanistic interpretability to do that kind of thing. Neil Nanda has a tutorial on it, so I thought about applying it here.
Yeah, great.
Yeah, nice work. Thank you for that. I'm really curious. I guess this probably hasn't been done, but I'd be really curious to see how you're looking into the attention heads compares to like what Rick found in hand constructing one. I don't know if either you or Rick has a comment on that.
Yeah, I think this is actually something that's interesting because I only looked specifically at the transformer that Adam trained. I didn't have a chance to look at what Rick trained. So, and also like the architecture of it is a little different. So something that will be very interesting to see if it replicates, right? If I could find like similar attention heads that like do the same thing in Rick's transformer, like if it generalizes, then that would really like it would really support like the CompMech hypothesis, right? Because they are like ultimately predicting the same structure. So obviously they ought to have like the similar circuits for it.
Yeah, thanks for your comment on that.
Thank you. Okay, I think I'll stop sharing now. If anyone has like one other question, then yeah.
Yeah, if there are no more questions, we can move on to the next one, which is, I've lost my chat window. Oh, it's unsupervised recovery of hidden Markov models from transformers with evolutionary algorithms. Here we see the slides.
But I think we don't hear you, Colin. Are you speaking? I don't hear you, at least.
Yeah, I don't hear you. Oh.
Hello?
Yep, great,
Yeah.
thanks.
Yeah.
Sounds good. All right, so yeah, hi, welcome to our hackathon presentation. I'm Colin, and my teammate Dylan and I worked on this together, and we're excited to share our results with you. So we tried tackling the problem of extracting an HMM from the transformer residual stream alone without knowing the HMM beforehand. So we were able to successfully extract which MES3 HMM a transformer was trained on, and this gives info on the transformer's underlying predictive process. So we hope that this will serve as a promising first step for extracting larger HMMs in a more general setting. So for background, we'll recap the relevant part of the foundational paper by Adam Paul and their collaborators. So they found that they could use a linear probe to map the transformer's residual stream activations to the correct MSP belief states, indicating that the transformer was internally computing information related to the MSP. So, I mean, this result is fascinating. So we learn a lot about the underlying structure of the sequence data and about what the transformer is doing internally with the HMM and the MSP. However, the HMM or the MSP reconstruction required us to already know what the HMM, to know what HMM generated the data in order to generate the targets for the linear probe. So in the wild, we'll only have the transformer and not the HMM or the MSP beforehand. So how can we find the MSP using just the transformer to get these insights? So in general, this task is extremely hard if we allow arbitrarily complex sequences in HMMs. As a first step, we restrict ourselves to MES3, the family of 3-state, 3-token HMMs that they reconstructed. And so these take two parameters, alpha and x, which control the token emissions and state transitions, respectively. If we know our HMMs are restricted to MES3, then the HMM extraction task is equivalent to determining alpha and x. So on the left, here's a reminder of what the class of MES3 HMMs looks like. This is specifically for x is 0.15 and alpha is 0.6. And on the right, we visualize the MSP belief geometries. So though we only have two parameters, the MSP geometries are pretty expressive and different. And so it's a non-trivial task to figure out an MSP, which is very similar to the true MSP. So I'll outline our overall process here. So the idea is that we propose a set of HMMs that we think could be accurate. Later we'll show how we do this exactly with evolutionary algorithms. And we train linear probes from the transformer to reconstruct each of these. So ideally, the lowest error metric indicates the correct HMM or gives us info on the best HMM around which we can further refine our candidates. The question is what metric to use. And MSE is not enough. We tried it initially, but found that the clustered MSP geometries would be easy to get a lower MSE for, even if it didn't match the sequence that the transformer was trained on. This is, we speculate, because MSE is concerned just with the absolute distance. And so we use R² to instead to account for this and kind of look at the relative scale. And so we do find that R² is highly effective. To get a clear picture, we generated a grid of linear probe R² values for many MES3s. So we just span the space of the parameters with some granularity. And we find that R² is pretty convex and easy to optimize for, with the maximum R² being very close to the original match. So for example, you can take a look on the left, x is 0.05 and alpha is 0.85. That's basically corresponding to the highest R², or it's very, very close to that. And there's no like false positives or anything for the most part. And so this makes it an effective signal for optimization algorithms, such as the evolutionary algorithm that we use. As an aside, I think it'd be interesting to see whether R² is similarly effective on more complex and many state HMMs. So for our overall process to obtain the original HMM, we use the evolutionary algorithms. These are optimization methods that iterate through generations and select the population for each generation based on a reward signal. So in this case, it's R². We use evolutionary algorithms because, unlike gradient descent, the reward signal doesn't necessarily need to be differentiable. So here it's difficult, though probably not impossible, for us to compute the gradient of R² with respect to the HMM parameters, since R² is a function of the transformer activations, which they're very complex and like a function of all the parameters in the transformer itself. So on the graph, the real parameters are marked with an x, and the parameters that actually maximized R² is a dark circle, and each subsequent generation is plotted with a different color. So you can kind of track these generations and see that the evolutionary algorithm is converging towards the correct values for X and alpha on both the MES3 setups within 5 generations. So for example, we contrast this to just like randomly searching 15 different points, and I think we can reasonably argue for this being a lot more efficient, especially if we would need to do it in higher dimensional space. And this is the same information, but with a different transformer, and thus, has a different optimum for what the ideal MES3 is. So overall, we're able to extract an HMM that is very similar to the true matching HMM. We're quite excited about this result because it gives a preliminary indication that we can actually extract the original HMM and MSP corresponding to the transformers data. And this tells us a lot about the underlying structure of the transformer, or like what it's doing. But still, the problem that we were capable of solving within this short time frame was it's a very low dimensional problem, and we want to note some important caveats and potential future directions. So one benefit of this analysis was that we knew that the HMM was generated by MES3, so we only have to iterate over the 2 parameters that generate the HMM. Since the parameter space for unstructured situations would be far greater, like for 3-state 3-token, I think it should be 24 free parameters. The amount of computation required by the search process would, also increase, and it might. We want to find like more tractable methods, or see if this scales. And for the search portion of our research, we deliberately used an out-of-the-box evolutionary algorithm with no frills, just to demonstrate the robustness of our R² reward signal. Downstream research on the optimization approach could look at more specialized optimization. And also, in theory, the R² reward signal should be differentiable, so we should be able to run gradient descent with it. And the convexity and smoothness of the R² reward signal makes us pretty hopeful about being able to do this. Okay, so that's it. Thanks for listening to the presentation, and any questions?
Great, thank you. Yeah, very cool. I think, finding ways to find belief state structures in the residual stream where we don't know ground truth is obviously very important, especially as we go forward and we want to apply these to more real systems. I was wondering if you had any thoughts about kind of how much of a limitation it is that one has to choose kind of a model class within HMMs. Like you need it seems you need some kind of family of HMMs for this method.
Right, absolutely. So this is like, I think the main limitation that we're working with is like a toy problem of families. I think in the unconstrained case for arbitrary 3-state 3-token, we would parameterize it with like there's like 27 like values in the transition and emission matrices, right? And so like 24 of those are free. So if we were to just like naively generalize this, that would be a lot more parameters. And I think we're leaving that as a promising direction for future work. And in even higher dimensional space, if we have like, real sequences that LLMs are trained on, those HMMs have like countless states. And so we will need to find some way to see whether these approaches generalize, probably not without some major modifications. So that's something we're hoping that this will set the stage for.
Oh yeah, that makes sense. Yeah, another thought that just kind of came to mind is maybe we can use kind of our a priori knowledge about the structure of natural language in some way to kind of restrict ourselves in certain ways, or whatever a priori knowledge we have about certain computational tasks that we're interested in. Maybe that could also help.
Yeah, I think so. And if we wanted to constrain to a certain class, we could at least like try to find the closest HMM within that class according to our R² metric, and try to see something similar.
Cool. Any other questions? Okay, if not, then thanks again to the presenters, and I just want to extend another very sincere thank you to everyone who participated in the hackathon. Yeah, it was super inspiring to see everyone work on it, and even just to talk and get to meet all of you for the weekend. Yeah, so, and everyone should be like super proud of themselves, since it's yeah, really impressive how much was done. We will be getting back to you within a week after we look through and discuss and think more about who the winners will be. So I'll take it from there. Thanks again, everyone.
Yeah, thanks. Just like to echo Adam's gratitude that we're really excited to see the work. You know, that the effort that everyone's put in has pushed the boundaries in ways that we've been curious about, and also ways that we didn't even think to be curious about. So really grateful for you all. And yeah, looking forward to interacting more in the future.